Yeah, good evening, Javier. And good evening, Srita, and good evening, Javier.
Good evening, sir.
Yeah, good evening. So, today we'll be starting with mechanical properties of fluids. Okay. So, see, with fluids, we see certain static properties. First, we study fluids at rest, that is the static properties. And the second, we see at the fluids as motion, fluids in motion, where we see the mechanical properties of the fluid. So once we look up at the static properties of the fluid, see, if you look up at the static properties, so in the static properties you find like the Archimedes principle, Pascal's law. Okay, all these are applicable. All these hold in the static properties of the fluids. Okay, so let's see. I'll just give a quick idea of the static properties. Then we will move on to the mechanical properties or dynamic properties of the fluid. Okay, so in the static properties of fluids. Okay. So in the static properties, what are the properties that we see? We look up for the pressure. Okay. So to find the pressure, can you tell how do we find the pressure of any fluid? Using the Pascal's law, we can find out the pressure and the pressure of fluid at any level. Or it is just a function of their height, so it is equal to H rho g. The pressure of a fluid is given by the formula H rho g, where H is the height, rho is the density, and g is the acceleration due to gravity. So the pressure at any point is a function of the height and acceleration due to gravity. We have a Archimedes principle. So according to the Archimedes principle, that we observe by the Archimedes principle that loss in weight of a body is equal to the up thrust, and it is equal to the weight of liquid displaced. So loss in weight, that is W2 minus W1, is equal to the up thrust, and this same up thrust is equal to the weight of liquid displaced. It is equal to weight of liquid displaced. So you get this weight. Did you get this? Loss in weight is equal to W2 minus W1. This is also equal to the up thrust and also equal to the weight of liquid displaced, which is equal to V rho G. So here V represents what are the, generally we remember the formula, but we do not know what are the different symbols it means. Here V represents the volume of solid submerged. Use volume of the solid submerged. That is your V. Rho represents the density of fluid. And of course, we know the value of G. Rho is the density of fluid. If you want to uh, correlate this with the uh, density of the substance. So you can do that also with the density of the substance. If the mass of the substance will be W2 by G, so its weight is W2. The mass of the substance would be W2, and hence we can write here. Suppose I want to link it, so I can link it some way. Since the weight of the liquid will be equal to mass multiplied by G, and mass can be given as V multiply sigma, where sigma is the density of the substance. And here this V represents the complete volume of the liquid. So this V, we mark is, let's mark it as V dash, or let's write it as V1. So, okay, let V1. So I'm taking here V1 is the volume of the solid, complete volume of the solid, complete volume. So remember, V1 is the complete volume and V is the part of the volume or the volume that is submerged. So I can put here, if I put here, I will get a relationship between V1 and V. So here, generally we have some questions where we find how much volume, how much part of the volume will be submerged given the densities of the two substances, and you are asked how much part of the volume will be equal to, or how much part of the volume is being submerged. Okay, so all these things we will see here. We will be utilizing these two concepts. Hence, we will find the W1 also. The W1 will also be equal to mass. Mass will remain the same. Okay. So in this way, we can find out W1, the loss in weight, and then equate both of them, get a relationship between sigma and rho to find out a relationship between V1 by V. So here our target will be generally to find out V1 by V, which is the part of the volume that is total volume, and V is the part of the volume submerged. Or somewhere we may say it V by V1. So the part of volume that is submerged, and this is the part of volume that is you can say V1 is the part of the volume, uh, total volume. Okay. So using this, we'll get some concepts here. We'll get some ideas how it becomes once we go into the depth of it. Okay. Can anyone tell me if anyone knows the formula for this? Okay. Okay, fine. We'll see. We'll see to it. How it happens. This upthrust will be equal to V rho g. Then we can relate it. Now, apart from the Archimedes principle, we have Pascal's law of pressure that says that pressure is equal to H rho g. Then we have some surface phenomena. Here we have some surface phenomena. The surface phenomena. In the surface phenomena, we study about the surface tensions. When we study about the surface phenomena, we have a look at surface tension. So we see here surface tension and excess pressure in a bubble. So the soap bubble, these are the cases that we study. We also study about the Venturi meter and the manometer. Venturi meter, we study about the manometer. So these are the different concepts that we have to study while studying the static fluids. When we study the dynamic fluids, dynamics of the fluids, so let us see the kinematics or the dynamics of the fluid. So we have here dynamic properties. Okay. So in the dynamic properties of fluids, what are the different things that we observe? First of all the liquids or all the fluids, they provide a backward dragging force. Okay. There is a backward dragging force that exists between all the fluids. So the backward dragging force, it is given by the formula F equals to minus eta A dV by dx, where dV by dx is the velocity gradient, A is the area of contact between the layers, F is the backward dragging force, and eta is the coefficient of viscosity. So from here, we can also define the coefficient of viscosity. The coefficient of viscosity is defined as the backward dragging force acting on a unit area having a velocity gradient of 1 per second. So if you have the velocity gradient of 1 per second, so just 1 per second will be the velocity gradient, area will be a unit meter square, and then the backward dragging force, whatever is the backward dragging force, that will be equal to the coefficient of viscosity. Okay. So this is a one way. Then second, we have studied about here about the Stokes law. So we study by the Stokes law, the backward dragging force F is given by 6 pi eta RV. So the backward dragging force acting on any fluid is equal to 6 pi eta RV, where R is the radius of the substance, V is the velocity with which it is moving, and 6 pi is a constant, eta of course we know. So if a substance is moving through a fluid it will experience a backward dragging force. If it's not moving, then there is no backward dragging. If it is moving through the fluid, so it will have a backward dragging force, and it will also be proportional to the size of the object. Hence, we have the radius. So this is the Stokes law, which is applicable. This Stokes law, it is applicable for all the substances where we have, generally this is made for the spherical objects. We have considered while deriving the Stokes law, we consider a spherical objects. Okay. So this is the case. If you have objects of other shape, so you will have different values. Okay. But this expression holds for the spherical objects. So these are the two very important concepts where we may get some of the questions. Then the next thing we observe in the dynamic properties of the fluid. Okay, one more thing here. As we observe, if you see here, force is equal to 6 pi eta RV. So this is a force as we have studied in the case of friction. See, this is also a frictional force offered by the fluids. So this frictional force is offered by the fluids, whereas that frictional force we study in the case of solids. So that was the frictional force which depends on the load. Okay, it does not depend on the velocity. That friction where we have studied, that we have seen just F by R is a constant. F by R is equal to mu. Okay, so here our force of friction is directly proportional to just the load R or the normal reaction. Here the force of friction is directly proportional to the velocity. So you will have different variations of this. We will observe different variations. How can it be? How can the different applications of this are also there? Like force can be written as mass multiplied by d2x by dt squared, or you can write it as dv by dt. Okay. So m times of dv by dt equals some constant 6 pi eta r and v. Now, if you take this term to the other side, you get an equation here. So this you get m times of dv by dt minus 6 pi eta rv is equal to 0. Okay. So this you get a differential equation. Again, we can still make it more differential by putting the value of v. We can also write m times of d2x by dt squared minus 6 pi eta r and dx by dt to be equal to 0. So now it's a differential equation which can be solved further. Okay. So we'll move further. We'll see wherever it's required. So this is one of the concepts. Stokes law is very important. Mostly you'll find questions from the Stokes law. So in the dynamic properties, we study about the coefficient of viscosity, which is given as the backward dragging force acting on a unit area with the velocity gradient of 1 meter or 1 per second. So the velocity gradient should be 1 per second, and hence you have that backward dragging force given by M. The backward dragging force on an object which is moving through a fluid is given by 6 pi eta RB. Then in the dynamic properties, we have a very important concept, that is Bernoulli's principle. So here we have about the Bernoulli's principle. What does Bernoulli's principle tell us? Bernoulli's principle, it gives us, we have these two very important, Bernoulli's principle and the equation of continuity. First, we will discuss about the equation of continuity also. The equation of continuity states that for a laminar flow, we have A1 V1 should be equal to A2 V2 for the laminar flow. And if the flow is turbulent, not laminar, it's turbulent, so then this equation will not. Okay. And here we have put certain assumptions. Now Bernoulli's theorem. So Bernoulli's theorem, it states that the sum of the potential head, kinetic head, and the pressure head is a constant. Okay. So we give here the sum of potential head. The potential head is, we write 1 by 2 rho v squared. This is the kinetic head. Plus you have GH plus GH is the potential head. Rho v squared is the kinetic head. So the sum of potential head, kinetic head, and the pressure head. Okay. So the pressure head is just your H rho. So it should be a constant. It is a constant. So using this, if you increase the velocity, so you will have a decrease in pressure. Sorry, it's P, not H rho, it's P here, pressure factor. So we observe here, if you follow some increase in velocity, if you increase the velocity, there will be a fall in pressure, right? If you increase the velocity, there will be fall in pressure. If you increase the pressure, there will be fall in velocity. So it's because of this, we can explain certain phenomena like the thatched roof being blown away, airplanes taking off. Okay, all those phenomena, they can be explained using this Bernoulli's principle. For example, you have those thatched roofs. So if fast moving, if air passes through it with certain velocity, let's say v. So with this v, there will be low pressure here. You will experience a low pressure, and inside this you will experience a high pressure just because of this Bernoulli's principle. Since here the wind is blowing, had the wind not been blowing on both the sides, the pressure would have been the same. Now if the wind is blowing, so due to the blowing of the wind, there is a velocity, and hence because of this, there will be a lowering of the pressure, since the sum total has to be a constant. Since the sum total has to be a constant, so therefore we give our velocity. If we have increased the velocity, so pressure has to decrease. There has to be low pressure, and here we have high pressure. So this thatched roof or whatever, it has to be blown away. If sufficient pressure builds up, so it can blow away. Right? Similar way, we take for the aerodynamics also. So Bernoulli's principle has a wide application. We'll also see the equation of continuity, also the Reynolds number. You should be able to recall the Reynolds number, the different values of the Reynolds number. Okay, at the different values of the Reynolds number specifies that at what value a fluid will become, or the flow of a fluid will become from laminar flow to a turbulent flow, or will it be a turbulent flow or a laminar? Okay, so can anyone tell me when do we have the fluid as a laminar flow and turbulent flow? Yes, anyone remembers? See, if you go for searching for the Reynolds number, there through NCRT you will find some Reynolds number. If you are looking for some Google, you will get something different values. Some other books will specify you some other values for the Reynolds number. Okay, so the Reynolds number is different for different cases. You will not get the same, and we prefer here the NCRT, whatever NCRT says about the Reynolds number, that we consider to be the correct. Okay. So just must refer the NCRT here. So I hope you have understood about these dynamic properties and the static properties. Any doubts to anyone? Yes.
No, sir.
No. So can we start with the questions? Can we start now? Let's see the questions. And in between, if we have some requirement of any other concept, I will be giving you during that question. Okay. So it's not possible to give everything in just this half an hour, since you know almost all the thing. I'm not going into the detail back. Okay. Here you have a okay. One more thing is there, just I forgot. That is the terminal velocity. Yes. You may get a question from this concept also, the terminal velocity. So what is the terminal velocity? Yes. Yes. The maximum velocity acquired by an object moving through a fluid with constant force. So if you have any object which is moving through any fluid, but it's moving with a constant force, so the object attains a maximum velocity beyond which the velocity of the object does not increase. Okay, that means the effect of force is no more zero, no more there. The forces are balanced by the backward dragging force. Whatever force act on the substance, so it will be equal to the backward dragging force, and hence the object will attain a terminal velocity. Okay. So what are the two different concepts that are utilized? If you observe in the books give you some formulas regarding the terminal velocity. So actually what happens here in the case of the terminal velocity, let's say you have these layers of air, and through these layers of air you have a solid substance which is falling through. So let's say you have this solid which is falling through this. Now the forces which are acting on this, one of the forces that acts is the downward weight of the object. The other force that acts is the upthrust. The upthrust. The second force that acts is the backward dragging force. So there are two forces which are acting on the upward direction. On the upward direction, you have your force F, which is your upthrust. You have a force F, which is our backward dragging force. So the backward dragging force is given by 6 pi eta RV. So these are the two forces which are acting in the upward direction. Whereas in the downward direction, you have the downward force as mg. So if you get both of these equal, okay, once you get both of them, add these two forces in the upward direction should be equal to mg, and then you can find out the value of the v. Okay, see the upthrust acting on the object we just studied will be equal to v rho g, where v is the volume of this, and the volume of this will be given by 4 by 3 pi r cube. So v rho, where rho is the density of air, multiply g. Now add these two, let it equal to mg, and you'll get the velocity. So let's see, you get mg equals 6 pi eta rv. Okay, so 6 pi eta rv plus you have 4 by 3 pi r cube rho g. Now, if you want to find out the terminal velocity, so you take this to this side, you get mg minus 4 by 3 pi r cube rho g should be equal to 6 pi eta rv. Now see, m is the mass of this solid. So mass of the solid can be written as volume of the solid multiplied by its density. Okay, so I can write this m as the mass of volume multiplied density, and volume will be 4 by 3 pi r cube. So you can obtain the expression here. We'll get 4 by 3 pi r cube multiply sigma, which is the density of solid, multiply g. And here you have minus of 4 by 3 pi r cube rho g equals to 6 pi eta rv. Okay. So now you can take out here 4 by 3 pi r cube g common. You can see here you will be just left with sigma minus rho equals to 6 pi eta rv. Now pi and pi cancel. One of the r cancels. You have your square. You have this 2. This cancel here. You have 3. So you will be getting here 2 by 9 R squared G, get sigma minus rho equals V. Equals, sorry, here you have eta. 2 by 9 eta, that is come to this side. You have the formula of velocity. So this is the formula of terminal velocity that you have studied in your in your classes. Now there is a simple trick to it. The trick is that you can forget about this rho, as the density of air is very small as compared with the density of the substance. The density of a metal ball is too heavy as compared with the density of air. So suppose if you are subtracting like the density of the metal ball, let's say it's 700, or not, it's even greater than 700, it's something about, let's say, 2000 or 5000. So from this 2000 you are subtracting the air of density of air, which is somewhere 0.00. So it's not making any sense subtracting the small number from it. Okay, so you can just leave it out, and the trick is that you can just use the formula of terminal velocity to be equal to 2 by 9 r square by eta G multiply sigma to be equal to the terminal. Got it? Your values will almost be same. Okay. Now let's just see some of the questions here. A spherical ball of radius 1 mm. A spherical ball of radius 1 mm and density 10.5 gram per centimeter cube is dropped in glycerin of coefficient of viscosity 9.8 poise and density 1.5 gram per centimeter cube. Viscous force on the ball when it attains a constant velocity is. Okay. So the viscous force is given 3896 multiply x multiply 10 to the power minus x Newton. The value of x is. So you have to find here the value of x. So the a spherical ball of radius 1 mm. Here radius is given as 1 mm and density is given as 10.5 gram per centimeter cube. This is your density of the substance. So let's write it sigma is 10.5 gram per centimeter cube. Is dropped in glycerin of coefficient of viscosity. So eta is given as 9.8 poise. And density of glycerin is given as 1.5 gram per centimeter cube. Viscous force on the ball when it attains a constant velocity is. So they have given a value of the viscous force, the backward dragging force. Now I want to find out just this value x. So using this information, whatever information is given here, can we find out the value of terminal velocity? Yes, Javian, can we find out the value of terminal velocity here?
Yes, I can try.
Okay. So just we studied the formula of the terminal velocity, 2 by 9 r square g by eta sigma minus rho. So this value will give us the terminal velocity. And once we obtain the value of terminal velocity, we have 2 by 9 r squared by eta. Here we have sigma minus rho. Just much. Yeah, Niharika. Niharika, are you able to unmute yourself? Okay, even if you are not able to unmute, you can use the chat section to reply. Okay. So see, we have this question: a spherical ball of radius 1 mm and density 10.5 gram per centimeter cube is dropped in glycerine of coefficient of viscosity. क्लास है बेटा, बहुत अच्छी ज्वाइन है। बढ़िया बना दूं, ये चावल बना दूं, चावल इससे सब खाए, इससे नमकीन चावल, मैं चावल नहीं बना तो टाइम लगेगा, हम आगे तो नहीं है साथ में। तुम बताओ क्या बनाओ? फ्राई बना दो, राइस बना, नमकीन चावल नहीं है, नहीं आएगा, अरे रखो, बस बच्चा कोई ज्वाइन ना हो जाए इसलिए बैठा हूँ 5 मिनट। घर में सुबह से उन्हें लग, उन्हें निकाल देना, उन्हें निकाल देना, चार 5 मिनट, 4। निकाल दूंगा।
आगे सबूत नहीं रहा।